Alright, this is Jack Jackson back again, and we're continuing our series of exercises on derivative concepts. And for this next little set of exercises, we're going to ask you to come up with a function, that is, come up with a formula for a function, like f of x equals some formula, and then maybe give a quick sketch of the graph of the function. And I'm going to give you some conditions, and we're going to make sure that these conditions are satisfied. Okay? So, for example, the first one here has f of x is greater than 0 for all x, f prime of x is less than 0 for all x, and f double prime of x is greater than 0 for all x. So what do those three things say about the function and the graph of it, and then can you come up with a function that fits those characteristics? Now, you should be able to think through your basic library of real basic functions that we reviewed last unit and that you've studied in your pre-calculus classes, and probably one of those basic functions, those elementary functions, one of them will have the right characteristics. Okay, so try to see if you can do this one right now. Press pause and come back when you're ready. Okay, well, let's think about this a minute. First of all, it says this is true for all x. So we're saying that the function, its derivative, and its second derivative are all defined for all x's. So that eliminates anything that has a limited domain of any kind. Domain is all real numbers. Since the derivative exists, it's connected, it's continuous. So this is a continuous function to start with. Secondly, the y values are all positive, so the graph is completely above the x-axis. Okay. So that's what the first part is telling us. The derivative is negative, so that means the original function must be decreasing. So we got a function that's above the x-axis, decreasing. And the second derivative is positive, so that says the original function is concave up everywhere. So, what does that look like? Let's see here. Does it look like, let's say it looks something like, here's the axis, right? It's got to be above the axis. It goes from forever left to forever right. It's decreasing, concave up, looks something like that. What function would look like that? Well, one answer is e to the minus x. Okay, and this should say e to the minus x would have that property, and that's not what we have graphed here, so we have e to the x graph there. Let's get the right graph here. So e to the minus x would work. Let's see, y equals e to the power, the opposite of x. Yeah, that looks pretty good. That looks like the kind of graph that we need. So let's just copy that graph, put that in our notes here. There we go. There's a pretty good example. So the function we came up with was f of x equals e to the power negative x. Now, is that the only one? Of course not. There's lots of different functions that look like this. But what characteristics does it have to have? The graph has to be always above the x-axis. That is, always has positive outputs. That's what this first part says. The second part says the derivative is always negative, so that the function is always decreasing. And the second derivative is always positive, so the original function is always concave up. So if you put that together, then you end up with something like what we have here. Okay? So see if you can come up with these. Now, if I give you a situation that's not possible, then say not possible. Otherwise, see if you can come up with an example. Okay, so f is continuous for all x, but it's not differentiable at x equals 2. Continuous everywhere, but not differentiable at x equals 2. See if you can come up with a function that does that. Come back when you think you have one. Press pause now. Well, this is possible. It could be continuous without being differentiable. In fact, there's basically two main ways that can happen. The first way it can happen is there's a sharp corner there. Typically, absolute value or a piecewise defined function would give us some kind of sharp corner. Absolute value, of course, is a piecewise defined function. So if we did, for example, f of x equals absolute value of x minus 2, that's going to give you a sharp corner there. And notice this function is continuous everywhere, but is not differentiable at x equals 2. It's differentiable everywhere else. Okay, that's the easiest one I can think of. That's not necessarily the only one. Another way we could get it is to be continuous but not differentiable at x equals 2 is to have a vertical tangent line. So this one up here with the sharp corner doesn't have a well-defined tangent line at x equals 2. On the one hand, secant lines from the right of that would be this line right here extended, okay, which would have a slope of 1. And from the left, we would have the secant lines coming in would be this line extended, and that would have a slope of -1. So the difference quotient, if you take the limit from the right, you get 1, and from the left, you get -1 as h approaches 0 from the right and left. Those limits are not the same, so the derivative doesn't exist. So there's not a single well-defined tangent line here. Here there is a single well-defined tangent line. It's a vertical line, though, but that does not have a well-defined slope. So there is no derivative. The derivative, the tangent line is vertical. So one way to get a vertical tangent line is like with the cube root function. So if we just take our cube root and shift it over 2 to the right, cube root of x minus 2, or x minus 2 to the 1/3, for example, will give us a nice vertical tangent line right there. And it means it's not differentiable. All right, the next one says, f is differentiable for all x, but it's not continuous at x equals 2. See if you can come up with such a thing, and come back when you've got your solution. Press pause now. Well, did you come up with one? Well, no, you couldn't have, because this is actually impossible. This is not possible. If it's differentiable at a point, it has to be continuous there. So if it's differentiable for all x, it's differentiable at x equals 2, and it has to be continuous at x equals 2. Anytime you have a discontinuity of any kind, the function's not differentiable there. So that was an impossible situation. That one can't be done. All right, how about this one? Let's see if we can just see it without seeing any of the solution. Okay, f of 4 equals 5, and f prime of x equals 7 for all x's. So the derivative is 7 everywhere, and specifically f of 4 equals 5. See if you can come up with the formula for that. Is there such a thing? If it's possible, come up with a formula of an example that fits that. Press pause now. Well, hopefully you realize that f of 4 equals 5 says that the specific point 4, 5 is actually on the graph. And when we say the derivative is 7, we're saying the slope of that graph is 7 everywhere. Well, a graph that has a constant slope is a linear function. So the only way you can have a constant slope is to have a linear function. So can we make a linear function with slope 7 and going through the point 4, 5? Yep, there's just one of those. So there's only one possible answer here. One way to write, there's a couple ways to write the equation. One way is this way. The slope, f, which is the derivative, is 7. X minus the x value, 4, plus, say call that a. And then this is f of a, the corresponding y here, 5. So this goes through the point 4, 5 and has a slope of 7. Now you could also do some other ways. For example, you could distribute the 7 here and combine like terms to get f of x equals 7x minus 23. And that's the slope y-intercept form. And the slope x-intercept form would be to take this right here and factor the 7 out. And so from here we see that x is 23/7 when y is 0. So 23/7 comma 0 is sort of where this one's centered up at. This one's centered up at 0, negative 23. And this one's sort of centered up at the point that we were given, 4, 5. So any one of those three are the same, and there are many other ways you could write the equation, but it's all the same. It's all the same relation. It's all the same function. So there's really only one possible answer here. All right, let's try one more here. If the derivative is greater than 0, the second derivative is negative, and the range is all real numbers. Notice it didn't say anything about the domain here necessarily. Okay, but at least where it's defined, the derivative is positive and the second derivative is negative. Can you think of a function that does, what would a function like that look like? And can you think of a function that you studied that looks like that? Okay, come up with one on your own, press pause now. Okay, so hopefully you realize that the derivative greater than 0 indicates that the function is increasing. The second derivative less than 0 indicates the function is concave down. Okay, so we've got a function that's increasing and concave down. And the range has to be all real numbers. It didn't say what we can do what we want on the domain. So one basic function is a logarithm. It looks like that, right? So at least of a log base bigger than 1. So like ln of x or log base 2 of x. Here's ln of x graphed. It has those characteristics. The derivative is positive, so this is an increasing function. The second derivative is negative, so it's concave down everywhere. And the range is all real numbers, but the domain's not. The domain's only 0 to infinity here. Okay, so that gives you a few examples of how we might think about what these things are saying about the graph, and then also we had to look back into our little library of elementary functions to find such a function that had those properties.